All right, good afternoon, everybody. Welcome back to Introduction to Physics, Day 2. So remember yesterday we just did our kind of introduction to the class, sort of the syllabus day, if you will. Just going through the background information about this course, kind of what to expect. And then I gave you time to do your background survey and your pre-test. So if you did not get a chance to complete those yet, please do so as soon as you can. That information really is beneficial for me in planning out these lessons for you. So based on the responses that I've received so far, it looks like a lot of you, most of you are going to be incoming freshmen. So freshmen in the fall, although we do have some students who will still be in high school at the time, and some who are current FIT students who will be starting in a different year other than freshman year. So we have a wide array of students, but a lot of you are incoming freshmen. A lot of different potential majors coming in, which is really exciting. That means that we have a great opportunity to learn from each other as well. Now, the thing about Physics 1 and sometimes Physics 2 is that it is required for most majors at FIT. So even if you're not a physics major or astrophysics or something like that, engineering, most students do have to take Physics 1 and Physics 2 at FIT. So hopefully this class will be beneficial for all of you. Also, from the background survey, I learned that a good number of you have taken physics in some capacity in high school, whether that was AP physics or just regular physics. But at the same time, a lot of you have not taken any level of physics yet. So hopefully this class won't be too fast paced for you, but at the same time, hopefully those of you who have taken physics before, it will be a good refresher for you. Like I said, this is going to be like an overview course. So we're not going to dive too far in depth into any of these topics because that is the point of Physics 1, which you'll probably take in the fall. Okay, so that's just a little bit of what I learned from you guys in the background survey so far. But today we are going to be starting our first topic. And let me go ahead and share my screen with you guys. And hopefully it will work this time. Okay, can you guys all see my slide? It says chapter 1, units, physical quantities, and vectors.
Yes.
Yes, thank you so much. Good. Okay, so let me just open up this chat. Oh, okay, we got a quick question before we get started. Yes, what is your question? It's in the chat. Is chemistry included in aerospace engineering bachelor's degree? Likely, yes. I mean, I had to take it as an astrophysics major. I had to take Chem 1 and Chem 2, as well as Chem 1 and Chem 2 labs. So my guess is that it is required for aerospace as well. Material science too. Enzo, are you asking like, material science is required for aerospace? Yes, cool. Yeah, I don't know the specifics of that particular program, so that's very helpful to know. Thank you, Enzo. Yeah, and that is something that your academic advisor would be able to better advise you on. So hopefully you guys have already been assigned to an academic advisor. You are welcome to email them, pester them with questions. That is their job. So don't feel bad for asking them questions. They know more than I do about the specifics. Okay, so let's go ahead and jump into chapter 1. So our first topic in this chapter is units and conversions. So a question that is sometimes jokingly asked about this particular topic is, what time will it be in 3.5 kilograms? That makes no sense. Okay, that should make no sense to any of us, right? What time will it be in 3.5 kilograms? It's just no, just don't do that. And so that's the point of today, talking about units and conversions, why they're so important, and how we use them in physics. Right, so here is our physics cat meme for today. Okay, so when we go through and solve physics problems, we're going to be following more or less this same outline every single time. Now, I won't explicitly mention this outline every single time, but I will be following this general guideline. So here's our strategy, IC. So the I stands for identify. We want to identify the relevant concepts. So is this a question pertaining to energy or projectile motion or momentum or a combination of things? That's going to be really helpful for you to identify, just so that we can know we're dealing with the correct equations. So don't skip this step. Figure out what topic within physics the question is even pertaining to. And then after you figure that out, you want to determine what the target variable is. So that's the quantity that you are trying to find. It's a lot easier to go into these problems if you know what it is you're looking for. That will guide you to the equations to use, and sometimes you can work backwards if you know what it is that you're looking for. The S stands for setup. So we want to set up the problem. So that means choosing the equations that we'll use. I highly recommend, whenever possible, that you draw a sketch of the scenario. And that way you can kind of wrap your head around everything that's given to you in the problem, what it is you're looking for, what the heck is happening. And a lot of the time, professors will give you partial credit on quizzes and tests if they can see your train of thought. So when you draw a sketch of the scenario, it helps the professors see how you're looking at the problem, and they will be more likely to give you partial credit if they can see kind of how you're thinking about it. The first E stands for execute. So we're going to execute the solution. We're going to go through all of the steps, plug in the numbers, figure out what we do know already, what we don't know already, and then start solving the problem. Now, the temptation here for a lot of students is to just stop at this E and not continue on to the next one, which is evaluate. But it is crucial that you take that time to evaluate your answer and ask yourself, does this even make sense? So you want to check your units, check your sign. For example, if we're trying to find the radius of the Earth and we calculate it to be 6.38 centimeters, that should not make sense to you, right? The Earth is clearly larger than 6.38 centimeters. So that means that your units are off. And yes, professors do care about the units that you use in your problems. They will require you most of the time to include units with your answers. So as you're writing the answer, if you see like a glaring error in your units, that's a good thing to catch during your evaluate. Also, look at the sign of your answer. Negative numbers versus positive numbers, they do make a difference, and you will lose credit if you put the wrong sign in your answer. Right? So
generally,
negative radius, that should not make sense.
May I say something?
Yes.
When it comes to negative and positive answers, if I remember correctly, in 3 to wait, I forgot. No, but generally, when it's negative, it's going right, and when it's positive, it's going
Yeah, so we'll talk through all of those scenarios of positive and negative, and it does depend sort of on your scenario. So we'll talk through all of that as it's applicable. I just wanted to throw that out there in our kind of outline of how we solve problems, to make sure that you check that as you evaluate your answer. Okay, any questions about this outline? Okay, I'm seeing some head shaking, so that's good. Okay, so here's just an example of a time when units were really important and were unfortunately ignored, right? So this Mars Climate Orbiter was launched in 1999. And then NASA lost contact with it 9 months later, right? So this was designed to investigate and map the evolution of Mars's atmosphere, its climate, the surface, and then communicate with the Mars polar lander that was already there. So that was its purpose, and then NASA lost contact with it. So when they investigated what happened, they found that it had burned up in the atmosphere. So its intended orbit was supposed to be somewhere around 90 miles above the surface of Mars, but it fell into the atmosphere at only 35 miles above the surface, right? So it completely missed its intended orbit and cost $193 million. That's a pretty expensive mistake, of course, so they wanted to know what happened. And unfortunately, what happened was just a mix up with the units, right? So there were several different teams that were working on constructing this, this orbiter. And some of the teams used metric units and some of the teams used English units. And so since those units were mixed together, the quantities did not make sense to the orbiter, and the result was an incredibly expensive mistake. Right, so units are important. I'm just gonna reiterate that again. Units are important. Pay attention to that. Pay attention to what you're given in the scenario that you solve. Okay, so the first question that we're gonna ask ourselves today is, what is a dimension? Right, so when we have numbers, that tells us an amount of something, but the amount of what in particular, that's our dimension, right? So a dimension has to be measurable in some capacity, and we measure it with units of something, okay? I know that's a very vague definition, but some common dimensions would be length, right? L, length. So typically we'll measure length in meters. Now, depending on where you live in the world, you might also measure length in inches or feet or miles or what have you. But in physics, our base unit, our standard unit that we will use is meters. Okay. Time is another dimension, T. We will measure that in seconds generally, right? It could be minutes, hours, years, but our base unit, the one we most commonly use, is seconds. And then mass is another kind of dimension that is given, usually given the variable m. And in physics, we'll measure it in kilograms. Now, chemistry often uses grams, which is also a metric unit. I know an English unit is a slug, but we will not be using slugs in physics. We will use kilograms. Okay, so those are our base units, and pretty much any other unit that we want to use is a combination of these base units. For example, we measure speed in meters per second. So that's a combination of those two for length and time. Newtons, which is kilograms times meters per second squared. So all of these other units that we'll use is a combination of these base units. Okay, so just a note to keep in mind for yourself as well. In math, variables can generally mean whatever you want, right? If you have an equation, 3x plus y equals 4, right? X and y are just, they're called dummy variables. It really doesn't matter what letter you use there. It could be 3a plus b equals 4. The letter is not what's important in math. In physics, however, these variables do matter, right? Mass is m, time is t, right? We don't want to kind of confuse those things and use a different letter for time. So there are some of these variables that are fixed in physics. Okay, capital A means amplitude. Lowercase a means acceleration. Capital V is voltage in physics too. Lowercase v stands for velocity, right? There a bunch of these units that are fixed for their particular dimension, and they all have their own units. So my recommendation to you might be, like, on a separate sheet of paper somewhere, just make a list as we go through these topics of the variable, what it means, and what units it's measured in. And that way, when you're done, you'll have maybe an equation sheet and then a sheet of all of the variables and what they mean. That will be helpful to you in the future. Okay, so when we use dimensions in equations, we need to be consistent with the dimensions and the units, right? So that question at the beginning, what time will it be in 3.5 kilograms? Makes no sense. You don't measure time in kilograms, you measure time in seconds, right? Or this example, this brick is 17 seconds heavier than that rock. Also doesn't make sense because we don't measure weight in seconds. So the units matter and they need to be consistent. Okay, so here are a couple of rules for consistency in our equations. If we're multiplying or dividing in our equation, the dimensions do not need to be consistent. So you'll see a lot of times in examples that we'll do in the future, we'll have equations where we multiply and divide things, and we can cancel units out if they're on top and on bottom, that sort of thing. But we don't need to have completely consistent units in those types of equations. However, when we're adding, subtracting, or claiming that two things are equal to each other, those dimensions and those units must be consistent with each other, right? So for example, dividing, meters per second, meters divided by seconds, that's totally fine, right? That's speed. And we see that on the top there's meters and on the bottom there's seconds, and those two things are not consistent with each other. They're not the same, but it's still a valid unit to have. For the second example, if we say 5 seconds equals 2 seconds plus 3 seconds, that makes sense, right? But if we say 5 seconds equals 2 seconds plus 3 kilometers, that does not make sense, right? Because kilometers is not the same thing as seconds, and so we can't add them together. Okay, so your units must be consistent when you're adding, subtracting, or claiming that two things are equal. Exponents will be dimensionless in our examples. Trig functions, whenever we use sine or cosine, that sort of thing, trig functions will be in degrees or radians and should have no other units. And then pure numbers are dimensionless or unitless. Okay, so the number 4 does not need to have a unit behind it. It can just be a number 4. Okay, so here is an example problem for you guys to just try really quickly. Determine which expressions or equations are valid based on their dimensions and their units. So take a look for that consistency that I was referring to. And just for your future reference, whenever you see that picture of the cat with his face in the corner, that means it's a problem for you to try on your own, and then we'll come back together and review the answer together. So I'm going to pause the recording here for just a moment and give you a minute or two to go through these equations and figure out which ones are valid and which ones are not. Okie dokie. Hopefully you had a chance to give all of those a try. If not, remember this PowerPoint will be posted on Canvas shortly after we finish the class, so you can go back and look at these. But here are the answers. Woo! Okay, so A, B, and E are all valid equations that you will see again in the future, because these expressions have units that match each other. Okay, so for part A, x, which is a distance quantity, right? So that would be measured in meters. Velocity is measured in meters per second. and time is measured in seconds, right? So when we have meters per second times seconds, those 2 seconds cancel each other out and we're left with just meters. And we can very easily add meters plus meters. That is valid. Okay. If we look at C, for example, right, we have a mass, which we measured in kilograms, plus 4, which does not have units. So we cannot add those two things together because when we add, subtract, or claim equality, those units must be consistent with each other. Okay, hopefully that makes sense. I'll give you guys some practice problems on Canvas as well to go through and give this some more practice if you need it. All right, another topic for today that is pretty important for physics is scientific notation. Now, my guess is that you've likely seen this quite extensively in your other science classes that you've taken, biology, chemistry for sure. If you've taken physics, obviously you've seen this before, but scientific notation is very important in Physics 1 and beyond. Why do we use it? Well, in physics, we often have to deal with numbers that are very, very big or very, very small. For example, the mass of the sun, if you are studying astrophysics, that is something that you will have just ingrained into your personality by the end of your first year. But the mass of the sun is approximately 2 times 10 to the 30 kilograms. Now, if we didn't have scientific notation, we would write that as a 2 with 30 zeros behind it every single time we use that number in a calculation. And that is just incredibly tedious. Same thing with very small numbers, right? In physics, we use the mass of an electron a lot, which is approximately 9 times 10 to the negative 31 kilograms. Right, so in that case, you would have a 0 point and then a whole bunch of zeros and then a 9. Again, very tedious to write out without scientific notation. So it does actually make our lives much easier if you can master the ways to write scientific notation. All right, so there are some other examples for you on the screen. The average distance between the sun and the earth, 93 million miles. The charge of an electron, right? These are all numbers that you will use fairly commonly. So here's how we write numbers in scientific notation if you have forgotten. So let's take the distance between the sun and the earth, 93 million miles. What we want to do is put the decimal point after the first non-zero digit. In this case, that would be a 9.3. And then we would drop the zeros that follow it. Now we write out, that's called our coefficient. That 9.3 is our coefficient. Then we would write out times 10. And then to find that exponent that goes next to the 10, we count the number of places from that decimal point to the end of the number, right? So if it's 9.3, we would put our finger between the 9 and the 3 and count how many places we have to move it over until we get to the end of that number. And in this case, it's 7. So 93 million miles becomes 9.3 times 10 to the 7 miles. We do have to be careful here. We're not just counting zeros in every case. And as we write the exponents, if the original number is bigger than 1, the exponent will be positive. If it is smaller than 1, the exponent will be negative. Right, so for proper scientific notation, that coefficient must be a number between 1.0000 and 9.9999 repeated, okay, for proper scientific notation. So here are some that I want you to give it a try on your own. How do we write the following numbers in scientific notation? There's the first one for you. How do we write this one in scientific notation? Give it a try.
Where could we find these slides? Is it on
It is not posted on Canvas yet, but it'll be posted immediately after class.
Oh, okay. I need to see that last slide for one more second whenever there's time.
Sure.
Do we just blurt it out or?
No, just like write it down on a scrap piece of paper. Or you can send me a direct message too, that's fine. Here is the answer that you should have arrived at. Right, so we put a decimal place, or our coefficient will be that first non-zero number, which is a 1. And then we count how many places we had to move that decimal point over to get it to be behind that first non-zero digit. And in this case, we moved it over 4 places to the right. So that means our exponent is -4.
I mean, it's scientific notation, but couldn't you just get rid of that one?
Yes.
Hmm.
Technically,
Yeah, I don't know.
yes. Can it be written as 10 to the -4? Sure. Okay, here's the next one. Give that a try. Write it in scientific notation. Good. I'm seeing some answers coming into the chat. 5 times 10 to the 3. Ooh, yes. Somebody also wrote 5e3. E is another shorthand notation for scientific notation, which is totally valid. Okay, next one. 0.078. What is that in scientific notation? Dun, dun, dun. Our answer is 7.8 times 10 to the -2, right? Because our decimal place goes between the 7 and the 8, right? After our first non-zero digit, which is the 7. And we moved that decimal place over to the right 2 places. So since we moved it to the right, the exponent is negative. And since we moved it over 2 places, it's -2. Okay, any questions about these examples? Cool. So again, this is probably a skill that you've learned in your other science classes in the past. I will have some problems like this on the practice worksheets that will be posted on Canvas today, if you want to just kind of refresh your memory on that. So when we want to convert back to standard notation for whatever reason, we just do the opposite of what we did to get to scientific notation. So if the exponent is positive, we move the decimal back to the right and make the coefficient larger. If the exponent is negative, we move the decimal to the left and make the coefficient smaller. Right? But in either case, we move the decimal the same number of places that we have as the exponent. So for example, the speed of light, which is approximately 3.0 times 10 to the 8 meters per second. If we were to write that out in standard notation, we move the decimal place to the right 8 places, and we arrive at this as our standard notation. Okay. The gravitational constant, 6.67 times 10 to the -11. In this case, since our exponent is negative, we'll be moving that decimal place back to the left 11 places to arrive at this final answer. Okay, so if you are not familiar with how to type scientific notation into your calculator, this slide will hopefully be a good reference for you. So I have my super old TI-84 calculator. I've had this since high school, and it has never done me wrong. So depending on what type of calculator you have, your numbers, I mean, your buttons might look a little bit different. So for me, my calculator has this EE button right there. And that's how I type in my scientific notation. So on your calculator or on your phone, you're going to want to look for some of the following buttons: EE times 10 to the X, or EXP. Right, so if you have an iPhone, you might see this EE button on your scientific calculator. If you turn it sideways, I don't have an iPhone, so in my calculator, I see this EXP button on my phone. This is the app that I have. So I have this EXP button. That's how I type in scientific notation. So get familiar with your calculator before you go into a quiz or a test, right? Figure out how to save yourself some time using that scientific notation button. Okay. In your answer, you might see it written out as like times 10 to the some exponent, but you might see your answer written out like this, 9.3 E7, which is the same thing as 9.3 times 10 to the 7, right? That E, whatever follows the E tells you what the exponent is. Okay. So solve this problem using your calculator. Just make sure you know how to type it in correctly. 2.34 times 10 to the 5 times 1.89 times 10 to the 7. What is your final answer on that? Give it a second and give it a try. All right, the number that you should arrive at, if you type it in correctly, will look like this. 4.42 E12 or 4.42 times 10 to the 12. They're equivalent, but that is the number that you should arrive at if you type it in your calculator correctly. All right, any questions about that?
I have a quick question.
Sure.
So my calculator shows like 4.4226. So we can write it to the 2 decimal places, or we can write as 4.4 into 10 to the power 3.
Yeah, so significant figures is another topic that some professors care about, others really don't care about. I included 3 significant figures here, so 2 decimal places, just because that is the precision that I was given in the problem. But some professors may have you just round to 4.4, and that is fine. Did that answer your question?
Yes, thank you.
Okay, great. Okay, next topic, metric powers of 10. So again, this is probably something you've seen in another science class. Hopefully this will just be a review for you, but you've probably seen some kind of table like this, right? So we have our multiplication factor. We have that written out as a power of 10 using scientific notation that we just went through. The symbol, which we would write before our base unit, and how we say that symbol, how we say that prefix before the base unit. Okay, so I have the entire table here written out for you, but I've starred the ones that are most commonly used in physics. So for example, this prefix kilo for kilograms, kilometers, that sort of thing, right? That's a common prefix that we use that means 1,000 or times 10 to the 3. And so we'll see that written in a unit as kg for kilograms or km for kilometers. Another common one that you'll see is centi, which means hundredth. And so that's a lowercase c. So centimeters would be cm. And there are 100 centimeters in 1 meter, because it's 100th. Milli is another common one that you'll see a lot. Millimeters, milliseconds, that sort of thing. So that gets the symbol m before our unit. And that's 1,000th, right? So times 10 to the negative 3. Other ones are common depending on what topic you're talking about in physics. So micro, for example, we use a lot in light, or when we're talking about wavelengths, we'll use nanometers or micrometers. If things are happening very quickly, we'll talk about nanoseconds or microseconds. But those are more specific to certain topics. These 3 that I have starred are the ones that you definitely want to have memorized for physics 1. Okay. So when we convert between units, this is another skill that is going to be very, very helpful for you in the future. The way that I learned to do it, and I think is a kind of logical, visual way to do it, is to set up these conversion problems as ratios. So if we say 1 minute is 60 seconds, we mean that they represent the same amount of time, that same time interval. 1 minute is the same thing as 60 seconds. So if we set this up as a ratio, you can see that would be like 1 minute over 60 seconds equals 1. They mean the same thing. Okay. So if units appear on the top and the bottom of our fraction, then they cancel each other out, right? So if you have the fraction 2 over 2, you can simplify that to be 1 over 1, right? You just divide both by 2 and you've canceled out the 2's, and now it's 1 over 1. The same sort of thinking applies to units as well. So when we're writing out our ratios, trying to convert between units, we want to write the ratio that allows us to cancel out any units that shouldn't appear in the final answer. And then once we have that written out, we multiply the numbers on the top of the fraction, divide by the numbers on the bottom of the fraction. This sounds sort of hand wavy at the moment, but we'll go through some examples of this where hopefully it will make a little bit more sense. Okay, so here's some examples. How many hertz, HZ is the unit hertz, are in 3,250 gigahertz? That's one of those prefixes that's not very common in most topics in physics, but in waves, sound, it is. Okay, so we're going to set it up as a fraction, keeping in mind that G stands for giga, which is 10 to the 9. So I'm going to first start by writing the number that I was given, 3,250 gigahertz. I want my final answer to be in hertz, not in gigahertz. So I'm going to set up my ratio so that gigahertz is on the bottom of the fraction. And that way, this gigahertz on the top will cancel out the gigahertz on the bottom. 1 gigahertz is 10 to the 9 hertz. So once gigahertz cancels out, we'll be left with just hertz, which is the unit that we're interested in. So when we take our numbers on the top, 3,250 times 10 to the 9, and we get, in scientific notation, 3.25 times 10 to the 12 hertz. Congrats, you just converted a unit. Woo! Okay, here's another example. How many kilometers are in 225 millimeters? Okay, so right there, there's two of our most commonly used prefixes in the same problem, kilo and milli. So those are going to be ones that are important for you to know. Let's set up our fraction. Right, we're given this number, 225 millimeters, so we'll write that first. From our table that I had on the other slide, we can remember that 1 millimeter is 10 to the negative 3 meters. And 1 kilometer is 10 to the 3 meters, positive 3. Now remember, I chose to write my fractions in this way so that millimeters on top will cancel out millimeters on bottom. Meters on top will cancel out meters on bottom. And we're left with just kilometers, which is the unit that we want for our final answer. Another way we can write this is without using scientific notation. So 225 millimeters, you can know the prefix milli, if you know millennium, millipede, those mean 1,000. So there's 1,000 millimeters in 1 meter. There's 1,000 meters in 1 kilometer, 10 to the 3. Okay. Again, we wrote it in such a way that millimeters on top cancels millimeters on bottom. Meters on top cancels meters on bottom. We're left with just kilometers, which is the unit that we want. And so in this top case, we would type into our calculator 225 times 10 to the negative 3 divided by 10 to the 3. Down here, we would type in 225 divided by 1,000 divided by 1,000. Same thing, we'll end up with 2.25 times 10 to the negative 4 kilometers.
I have a question.
Yes.
So in this case, oh, sorry, can you back? So for number 4, like we moved the decimal place over 3 more times and it turned it into 3.25 times 10 to the 12.
Mhm.
And then in example 5, are we moving it the decimal from the left to the right? So now it's -4, like 10 to the -4 instead of 10 to the -3.
Yes.
And how do we know how do we know like when to do that? Like move it from the left to the right?
So if we are making
'Cause-
our unit
Hmm,
smaller, right,
yeah,
going from a big unit to a smaller unit, then our number is going to get bigger. Because if you, I'm trying to think of a good example for this, other than just like the ones that we have. Okay, so you know kind of instinctively, hopefully, that a centimeter is smaller than a meter,
yeah.
right? So if we're going from a big unit meters to a small unit centimeters, we're going to have a lot more centimeters that make up our meters. And so our exponent is going to get bigger. The number gets bigger as the unit gets smaller. Right.
Okay.
In case 5, we're going from a small unit, millimeters, to a big unit, kilometers.
Yeah, so it's gonna be very small, but
Right, it's
large
gonna be a
number.
very small amount of kilometers, so our exponent gets negative, it gets smaller. Does that make
Okay.
sense?
Yeah.
Perfect. Any other questions? Okay, so just really quickly, I want to go back to this slide of our metric powers of 10, right? Because it is sort of hard for a lot of people to just look at a table and memorize it and remember everything that it says. But sometimes what can help with memorization is just to relate it to words that you already know. So for example, deca kind of sounds like a decade. How many years are in a decade? 10, right? So that's a multiplication factor of 10. Okay. You guys are like a technology generation. So for our like bigger units, you can probably think of computer storage as well. So would you rather have the storage of a kilobyte or a gigabyte or a terabyte? Like which one gives you more storage? That will kind of help you remember the order of these prefixes. So try to associate these prefixes with words that you already know from other contexts, and that will help you keep them straight in your mind. Okay, back to where we were. So we want to be careful here as we convert units because some of them are tricky. For example, how many square centimeters are in 400 square meters? If we have units that are squared or cubed or some other exponented, then you must square or cube your conversion factors as well. Okay, so 400 square meters. We know from our prefix table that 1 centimeter is 10 to the -2 meters. But since we're dealing with square meters here, we have to square that whole conversion factor, not just the unit, right? We square that number as well. And so now if we look at our units, this meters squared on top can cancel out this meters squared on bottom. But we still have to square that number, right? We're not completely canceling out the exponent when that happens. That exponent gets distributed to the number as well as to the unit. Okay, so that's why we end up with this 10 to the negative 4 as our conversion factor now. So our meters squared will cancel out. We're left with centimeters squared. So 400 square meters is 4 times 10 to the 6 square centimeters. Right, 400 divided by 10 to the negative 4 gives us 4 times 10 to the positive 6 square centimeters. So converting between English and metric units is a very similar process. It's just our conversion factors are a little less convenient, right? When we're converting between metric units, we're basically just dealing with powers of 10, right? 10 to the negative 3, 10 to the positive 3, 10 to the negative 6. Those are all very nice and convenient conversion factors within metric units. However, English units to metric units or vice versa do not have convenient conversion factors. Most of the time, professors will give you these conversion factors on a quiz or a test. And if they don't explicitly state it in the problem, you can go up and ask them and they'll, write it on the board for the whole class. Typically, I just either memorize them or I just write them in the corner of my equation sheet so that I know where to look for them. But for example, 1 inch is 2.54 centimeters. 1 kilogram is 2.2 pounds, and 1 mile is 1.6 kilometers. Okay, those are very common conversion factors that you might want to just memorize if you can. But you can see they're definitely not as convenient to memorize. Okay. But we're going to use the same process when we convert between these units anyway. We'll set up our fractions, our ratios that allow us to cancel out the units that we don't want and get us to the units that we do want. So here's our example. How fast are you going in miles per hour if you are driving 31.3 meters per second? Now this one is a little bit tricky because neither of the units that we have are the units that we want to end up with. So we have to go from meters to miles and from seconds to hours. So this process is going to be a little bit longer, but it's the same thing, just more steps. So we'll set up what we're given first. 31.3 meters per second or per 1 second. That's our first ratio. It doesn't matter if you convert your length units first or your time units. Pick your poison, I guess. So here I went with time, but we know that there's 60 seconds in 1 minute. And I wrote the 60 seconds on top so that the seconds will cancel out the seconds on the bottom. Minutes is still not the final unit that we want though. So we need another conversion factor of 60 minutes in 1 hour. And again, I wrote the 60 minutes on top so that those units will cancel out and we're left with the hours, the unit that we want in our final answer. Now we're not done here because we still have our unit of meters instead of miles. So now we'll convert our distances. We know that 1 kilometer is 1,000 meters. And again, I wrote it this way so that meters on top will cancel meters on bottom. And now our awkward conversion factor, 1 mile is 1.6 kilometers. So now kilometers on top cancels kilometers on bottom, and we're left with miles on top and hours on bottom, which is what we want in our final answer. So when you type this into your calculator, you'll multiply all of the numbers on the tops of the fractions and divide by the numbers on the bottom. So 31.3 times 60 times 60 times 1 divided by 1,000 divided by 1.6. And that will give you your final answer of 70.4 miles per hour. Okay, so it's the same process, setting up these ratios, canceling out our units that we don't want, It just took a little bit longer because we had to use quite a few conversion factors. The meters got canceled here in this step. 1 kilometer is 1,000 meters. Okay. Cool. Any questions about this problem? All right. So here's a problem for you to give a try, just really quickly. The distance from Earth to the sun is approximately 93 million miles. So here are our conversion factors. 1 mile is 1.6 kilometers. 1 inch is 2.54 centimeters. How many inches away is the sun? And I want you to write your answer in scientific notation to give that some practice as well. Okay, so I'm going to pause the recording. I'll give you about a minute to set up this problem, and then we'll come back through and go through the answer. Okay, so let's take a look at this, go through it together. So here are the ratios as I wrote them, right? We're given 93 million miles. We know that 1 mile is 1.6 kilometers. We write it in this way so that miles on top cancels miles on bottom. We don't want our final answer to be in kilometers though, we want it in inches. And our conversion factor is from inches to centimeters. So we need to go from kilometers to centimeters. I did that in 2 steps. You can do that in just 1 if you're familiar with your prefixes. But my 2 steps, 1 kilometer is 1,000 meters. And 1 meter is 100 centimeters. Now that we have our unit in centimeters here, we can use our conversion factor of 1 inch equals 2.54 centimeters. So if you take a look at my ratio and the things that cancels out, we have miles on top and miles on bottom, kilometers on top and kilometers on bottom, meters on top, meters on bottom, centimeters on top, centimeters on bottom, and we're left with our final unit, which is inches. So when I multiply 93 million times 1.6 times 1,000 times 100 divided by 2.54, we get 5.86 times 10 to the 12 inches. Okay. Now you might have written these ratios a little bit differently. You might have used your powers of 10, so 10 to the 3, 10 to the negative 2, that sort of thing. That's fine, as long as it gets you to that same final answer. Okay. I have one more problem for you to give it a try. I know we have just a couple of minutes left, but I want you to give this one a try, set it up at least before we end our class today. The world's largest cut diamond is the first star of Africa. Its volume is 1.84 cubic inches. Hint, hint, that is important. What is its volume in cubic centimeters and in cubic meters? Okay, so again, pay attention to those units, set up this problem, and then we'll come back together and I'll show you the answer. Okay, so that may have been enough time for you to set up one of those fractions, maybe not, both of them. But here is the answer, just to be respectful of your time. Okay, so 1.84 cubic inches. Remember, that means we need to cube our conversion factors as well. So if 1 inch is 2.54 centimeters, that means 1 cubic inch, we cube that conversion factor as well, right? So 1.84 times 2.54 cubed gives us an answer of 30.2 cubic centimeters. Okay. Similarly, if we want to go from our cubic centimeters to our cubic meters, then we again have to cube our conversion factor of 10 to the negative 2. So 30.2 cubic centimeters times 10 to the negative 2 cubed will get us into cubic meters. which is 30.2 times 10 to the negative 6, although that's not proper scientific notation. Proper scientific notation would tell us it's 3.02 times 10 to the negative 5 cubic meters. Okay, so if those give you a little bit of a challenge, I do have some problems like this on the practice problems that I'll post today. I'll be posting the answer key to those problems on Friday. And I want to leave you quickly with this bonus problem that we'll start off the class tomorrow with. So this would be like your homework if you choose to do it. Okay, so here we have the mass of an asteroid, which has a, well, we want to find the mass of the asteroid, which has a radius of 3.5 kilometers. And there are conversion factors. Okay, so again, this is our bonus problem. It is a challenge problem. I recommend that you give it a try, see how you do, but we will start class tomorrow going over the solution to this one. So to find the practice problems for today's topic, you'll go to our Canvas class page. Under files, you'll look in O1 units and conversion practice, and then I'll have a couple of resources there for you to try. Again, the answer keys will be posted on Friday, so you can check your work later on. All right, do you guys have any questions, comments, or concerns about today's lesson?
No questions.
Okay, great. Well, thank you so much for hanging in there for this extra couple of minutes. I know I kept you 3 minutes late. But again, this PowerPoint will be posted on Canvas very shortly after I end the recording today. And the recording will be uploaded to YouTube as soon as it processes and all of that stuff that it does. So you'll have access to the recording as well as the notes and those resources to practice. But I hope you guys have a lovely rest of your day, and I will see you tomorrow. Bye.
Thank you.